Let's go ahead and get started. I'm Christopher Hoffman. I'm a software engineer on the CephFS team at IBM, and going to be discussing bringing fscrypt to Userspace. Before I get started, let's see a show of hands. Who uses encryption anywhere in their data center right now? Okay, a good number of hands. So maybe I can convince you to adopt fscrypt going forward as well. So let's take a look at the overview of fscrypt. It comprises of a set of libraries that are present in the upstream kernel. It enables the transparent encryption of a file system. So completely transparent of any type of operations. It's widely supported within the upstream kernel on various file systems, ext4, e2fs, as mentioned earlier in the CephFS talk, kernel client, and then also the Lustre file system supports it as well, which is another distributed system. So looking at how to interact or set up fscrypt, it's done by setting encryption policy and adding a key that gets mapped to a directory. It has to be set up on a completely empty directory. So things like encrypting or setting it up on a directory that has contents already, it doesn't do inline encryption. One major feature of fscrypt is within a file system, you're able to have different types of, on a directory, for instance, directory 1, some policy and a key, and then each different directory can be tunable, which allows for multi-tenancy, and with encryption enabled, there's various ways to actually interact and enable fscrypt, various CLI tools that are supported, fscrypt CLI, a more lower level fsctl CLI command, and then xfs tests, which supplies xfs IO. And these interact with IOCTLs, IOCuddles. They are a way to interact with a file system for folks that are unfamiliar, that aren't the typical read-writes. So taking a look at how encryption works, file names and data contents are both encrypted. There's a wide variety of ciphers that are supported for the file names, all the way up to 256-bit, all the way down to Atium, which is a slower one to be used on low-power CPUs. The encrypted file names are stored as the name in the D entry, and then also there's unallowable characters that can end up there, such as slash, a null character, and also the name can be longer in some cases than what's allowable in POSIX of 256 or 250. So in order to display it properly, alternate names are used, which is a base 64 encoded name that's only allowable up to 255 characters. And then the other metadata that's present, type, size, mode, X adders are all unencrypted. Data contents also have a wide variety of ciphers. In the previous slide and the top slide, or this slide, excuse me, 256 is recommended unless you have some other requirement. Each file has its own key that's derived from the master key that's mentioned in the previous step. And then from there, each block within the file, so think of it as a fscrypt block that's 4K, is encrypted differently based off the key and the index of that block. And then also fscrypt explicitly doesn't support collapse range or insert range, excuse me. And encryption in general, makes offline attacks harder. If one key is discovered, you don't have the keys to the kingdom. With encryption in general, though, there's going to be some sort of padding that goes on, kind of read and write penalties. So any write that's not on a 4K boundary on the block boundary will have some sort of padding. So how it works is if you have like let's just keep it a small file that's 2K, it'll end up actually writing 4K. So it does that so it's not visible to the user if the file is, or the data contents, so they can't infer anything from it, essentially. And then also read, modify, write workloads are going to have the read amplification and write amplification. Taking a look at access semantics, which is a concept within fscrypt to allow the directory to be locked down or what they deem unlocked. The locked mode allows the encryption policy to be present, but the user or admin hasn't set up or added the master key yet. So metadata can be read using various supported calls that you would normally use. You can traverse the tree. You'll see a lot of alternate names everywhere, but you can get kind of an idea of the directory structure. If you're able to do regular unlinks or removes in the lock state, you're able to do it as well. You're able to see which files have symlinks, but if you do a long listing of it, it'll just point to something that's not useful because it'll be an encrypted version. You're unable to open and to read and write data, and also you can't truncate files. And then when you are in the unlocked mode, it's when the policy and key are both present on the client, and then it operates like a regular CephFS directory. So in order to paint a picture of what work was done to bring it to user space, I need to go back in time a little bit. fscrypt support was added to the kernel client a number of years ago now by various folks. If you want to have a more in-depth update on that, there was a talk a couple years ago at CephCon. Some of you might have seen that. But from a high level, that work was comprised in 3 parts: the kernel client, the MDS, and then limited user space client work. The CephFS K client became fscrypt aware, so it could do various workloads of read write, figure out there's a notion of different types of sizes of what the user sees, the logical sides, and what's actually written to the OSDs. In order to do that, there were some various variables that were added as extended attributes. So fscrypt auth, which is a X-header that stores the fscrypt context, so encryption modes, so the policy, and then the key ID, and then also the nonce for the file itself is there, and then fscrypt file, which stores the logical size. And then also there was a concept introduced of fscrypt last block. It's a common problem that is seen in different types of encryption implementations, but it was added. This addresses the smaller truncate case, and I'll speak about that more further later. Taking a look at user space, there's been very little at this point in time work done there. So what was added is be able to view file names as alternate names, added partial support for logical size, and then also there's no access semantics, so the rules of locked and unlocked don't apply if you're accessing it from Fuse currently. And then you can do things also like writing to the file and corrupt it. After that, there were numerous improvements and fixes that were underway. The big one here is the adding protection from the clients without fscrypt support. There's an active PR open right now that's attempting to block writes, moves, etc., that type of thing. But we're still working out all the fine details on how to enforce more semantics. And then there were a few things we missed, alternate name in all the places that needs to be, relation to snapshot. So if we take a look at fscrypt and distributed clients, on the left we have the clients, client 1, 2, and 3, and then on the right is interaction, or the MDS, and then in the middle is interactions with the MDS. Upper left shows here fscrypt enabled clients. So we can think of it as the kernel client or the user space with it added to it, which I'll discuss further. Client 1, for instance, has the key set up, so it has regular unlocked access. Client 2 did not set up the key here, so it has everything that locked implies. And then I wanted to add here on the bottom, client 3, from the viewpoint of the PR that we've been working on. The client doesn't have any notion of how to add a key, how to remove it, locked and unlocked, but there's various things that are blocked at this point in time. That's an improvement from the alternative. So motivation of adding fscrypt to user space is first and foremost feature parity. So we're wanting to be able to make this feature as accessible to various types of consumers or users of CephFS to have an uptick in adoption. So there's various key advantages of user space. It's not unique to this project. Faster iteration on bug fixes, faster debugging, or easier debugging in some ways of various components. There's been discussion on NFS Ganesha and Samba to support fscrypt as well, again opening it up for wider use cases. And depending on your various interest and use case, you may be able to eliminate using stacked file systems listed here, encryptfs, encfs, or other inline encryption mechanisms. So now I'm going to speak about the actual setup of and implementation of user space at fscrypt. It's going to be two parts. The first part is core functional work. The initial work was done by Yehuda. Things like the equivalents that are in the kernel were added, crypto, keyring for encryption, decryption, etc. Added support in Fuse for IO cuddle, support the various CLI tools, routines to support different types of IO, async, sync, added test structure for the various new features, and then various odds and ends, defined APIs in libcephfs, file capabilities, handled various truncate cases, link handling, and whole support. One thing that was ran into is we had some problems with the IO cuddles. Definitions were not correct in the kernel. So specifically the set and get policy, so in an IO cuddle definition, you can define various things, and you also can define if it's input or output, so read or write, or both in some cases. And what you would expect for set encryption, it'd be you're receiving something from some inputs would be input. Unfortunately, it's output, and then the get is also flipped. This wasn't a problem in the kernel itself because a lot of different types of restrictions are bypassed because there's apparent trust. But unfortunately, in Fuse, these definitions are strictly enforced and restricted. Inferring from a discussion on the mailing list in the kernel, there was my interpretation on it wouldn't be fixed or changed because there could be various versioning and user space things that compile with the older versions. So what we chose to do was create new IO cuddles, define new set and get as listed, and then also we use fscrypt CLI extensively within our tests in pathology to validate CephFS, and so we needed to update fscrypt CLI to be aware of this limitation. So second part is when I took over this project, what I first and foremost wanted to do was make it true to the fscrypt specification. There's a long defined document, ever evolving in the Linux kernel doc. I wanted to, in order to do that, and since CephFS already has its implementation with the kernel, I wanted to use that as a source of truth. So implemented access semantics as defined earlier, added tests to ensure specific security is kept at present, but then also in the future it doesn't change, so we don't have some sort of leak. I added our support for multiple unlock claims. That's the notion of, if you go back to my example from before, you have directory 1 that's enabled with fscrypt. User 1 can unlock it, user 2 can unlock it, so there's multiple unlocks that happen, and that's so the directory can't get locked from underneath it if someone already has a claim to it. And then also, there were a few odds and ends with the IO cuddles that I needed to populate the output flags. Next, I looked at ensuring existing fscrypt tests that were already defined within our test suite for metadata and data work on this version, and then I added some on my own for interoperability with concurrent clients. So let's go through of making the test work, so essentially validating the data and metadata path. So we have a set of tests, FS tests, that we use to do that. Various utilities are used, such as FFSB, PJD, dbench, a long list of them. With each utility, it's very common that they'll do a git pull, so pull down the source code, and then build the actual utility locally. And this is where a lot of the common read and write paths were edge cases were discovered. And this is, as you're going to be able to see soon, it's each step of the way encountered an issue. FSSB failed initially just on the git pull. This was an issue with, I was using a older base, again, with my code. So essentially, it was about 6 months older than the newest upstream version, and there was a bug that was introduced that intersected with this path, but it was subsequently fixed. So a rebase was able to solve that problem once I identified that's what it was. Next step is configure. That failed as well. There was a autoconf type operation that extended a header, and the file size wasn't being updated, so it looked like the smaller version. And then there were a wide variety of every step along the way. GCC failed. The actual FFSB suite, or utility, excuse me, had issues on overwrites with seek. And then overwrite as well here with a smaller file copied over a larger file. And then there were various read failures as well. taking a look at proving out the metadata, I used PJD. There were a number of things that were uncovered. Outshone caused a link to become encrypted with the wrong key. So essentially, when a link was created, it used the parent directory key instead of the new created per its file, that it should have its own unique one. And then there were various truncate issues related to logical and real size. File sizes rounded up to fscrypt block, size after write. So for instance, if you write 2 kilobytes, doing a stat, you'll get 4K back when you should actually see the logical size. And then as well with truncate, similar types of behavior. And then there was this really unique one where it was a Boolean logic statement, so a type of, during the read modify write workload, where if it ended at the boundary, that was causing some seg faults. And then, as shown on this slide, there are a wide variety of utilities used. Once after the first 2 were used, luck had it that all the other ones for data path worked without issue. So it proved out that reads and writes work, but also simple workloads, single client work as expected. Very confident that its single client workloads are stable at this point. So then I started to test and validate interoperability between clients. So now looking at not only metadata, but also checksumming that the data is correct. So there's various tests you can do, fuse to fuse, or a different client, fuse to kernel client, or the K client to K client. Also wanted to prove out caching was behaving correctly. So ran into a lot of truncate issues, make sure that's working across clients, make sure the cache is the right version, make sure it gives up the right to cache so other clients can see the new version. And then also introduce strided writes into this test suite. Each test, a client takes turn writing a little section of what I defined to a shared file. And then after each write sync, so the data doesn't get clobbered. So there are 3 types, strided writes within an fscrypt boundary, so little tiny writes under 4K, strided writes on fscrypt boundary, ideal type of workloads of 4K over and over, and then really unfriendly type of workloads, interleave strided writes that are overcrossing block boundaries. At this time, if I go back, at this time the current strided writes are still being tested, and the validation continues. Next thing I implemented was the fscrypt last block. So this is needed when truncating an encrypted file to a smaller size. Typically, or traditionally, the truncate happens, a client sends, I want to make this file this size, the metadata server does everything in order to truncate it, etc., and then gets the new size back. So this is typically a metadata operation that was changed into a 2-phase approach. Traditionally, metadata must be updated, but data also must be provided in the truncate request of the last block. So what changed for each component? The client provides encrypted last block resized to the new size, and then also the MDS does the write of the last block. So let's take a look at a sample case of this. So we have up here a truncate smaller case from a file that's 24 KB down to 22 KB. There's a file here represented as foo, 6 even blocks of 4K each. The last one here is the last block. So if we take and focus on that, we decrypt it, we get the actual real data of it, and then we only copy, in this case, half of it, which is the 2. And then we re-encrypt it, pads up again to the 4 kilobytes, as mentioned. And then that file we have, or that data block, is sent via a truncate call. This is the enabled fscrypt client that has the key and unlock mentioned before. It does its multi-step approach of truncate, the MDS receives it here in step 2, and then it writes it to the OSD, and it doesn't actually return the truncate call until that's persisted. So taking a look at, from a high level, various ways to use it, fscrypt CLIs or use various IO-CTLs as previously discussed. There's 4 main ways to interact. fscrypt init, which sets up the operating system that you're on with various config files and things you can change. And then fscrypt setup, which is file system level configuration. It sets up a .fscrypt directory, which has various files in there for keeping track of keys. And then fscrypt encrypt, which does 2 things. It sets the policy that we spoke about earlier, and then also adds the fscrypt key that is needed to unlock it. And then you are able to lock and unlock various directories with those commands. Taking a look at libcephfs, we defined the equivalence of that. You can add fscrypt key, remove key. You can get the key status to see if it's present to determine if it's locked or unlocked, and then set or get policy as well. And as you can see too, it's v2, so that's the recommended version. So what's next and what's the finish? This is about a 1.5 year long project so far. We need to finish and get the Userspace implementation emerged upstream. And then looking forward on what are some things that we can add in the future to it. The first is there's been a notion of how do you back up a encrypted file system if you don't have the key. So you have to come up with an interface to back it up if you're an admin or power user. So you're able to do that via this mechanism to allow admins to back up multiple enabled directories within the same file systems. There's been various discussions on the upstream kernel, because again, we're based off of the actual fscrypt spec defined there, and we don't want to get ahead of them, but also we have our requirements as well. So there's been discussions, but no implementation at this point. We need to finish up that PR I linked earlier to enforce semantic enforcement, and then eventually get to performance testing to see what overhead is introduced in fscrypt itself, and then also again compare between the 2 different client types to ensure to see if there's any improvements we can do with that implementation or that one. And then from here, open up to questions. Yes, please.
So at the beginning you mentioned you need to perform all operations on a 4K basis. That's what I understand. But how do you know when you perform a write, and you said you pad write, how do you know that there's not already existing data, you know, that you could read to kind of fill up the block?
Yeah, there will be, it'll go through the read modify write workload. If there's a object that exists for that, it will read it. If not, it'll know not to, and then
Okay, so
and then write.
so if there's something you read before that, so you have like a, so you always perform a read, or you know before?
On an override, you will have to, yes.
Okay. Oh, thank you.
We have one over here, and then you next.
Yeah, thanks for your presentation. I was wondering, have you tested with performance? So when you have a file system without fscrypt, and you upload the file and then do it with fscrypt, what is the performance impact that you have then? Have you tested that?
That's on our to-do list that I briefly mentioned at the end.
Yeah, it's done by the client, if I understand it correctly. So it depends on the hardware for your client, right? So yeah, I was wondering what is then the impact if you have an encryption layer, and what will then be the impact for uploading, decrypting your file, etc.
Yeah, there will be some sort of overhead because you'll have to read the bloated data all the time. But also so you're asking if we tested it, and we haven't yet.
Okay, thanks.
So the question was, do we support the subdirectory encryption? So there's various levels you can encrypt within Ceph. You can do it at the subvolume level, which encrypts the root FSFS of the file system. But then within that, if you don't do that, you can have directory 1, 2, to whatever, and you can encrypt each one individually, which allows for the concept of that I briefly touched on of multi-tenancy, etc.
Which lab you used to do the encryptor or the decryptor operation? OpenSL or?
So if I understand, you're wondering what library we're using to encrypt, decrypt.
Yeah.
I feel like I should know this because I've looked at it, but I'm drawing a blank right now.
Okay.
It's not anything that's not just a standard one that's in C++. All right, if there's no further questions, thank you so much.